Hello and welcome to this presentation of the bus matrices interconnecting masters and slaves in the STM32H5. This slide describes the 32-bit bus matrix of STM32H5 6X and STM32H5 microcontrollers. Masters are located at the top of the figure, while slaves are located on the right. The bus matrix provides access from a master to a slave, enabling concurrent access and efficient operation even when several high-speed peripherals work simultaneously. The STM32H5 ARM Cortex-M33 core is optimized for execution thanks to an instruction cache with direct access to flash through the fast master port. The AHB5 multi-layer bus matrix in the center of the figure interconnects 13 masters and 10 slaves. In order to offer a high bandwidth path to refill the instruction cache, a direct 128-bit bus connects the fast port of the instruction cache to the flash interface. The bus matrix features a fast bus multiplexer used to connect each master to a given slave without latency. For the same master, other slaves undergo a latency of at least one cycle at each new access. You can see that a unique fast bus multiplexer is present in any particular column. It selects the default slave for the related master, which is accessed without latency, for instance the FMC in the iCache slow port. Access permissions of memories are controlled by the block-based memory protection controller, or MPCBB, or watermark-based memory protection controller, or MPCWM. Note that the flash controller embeds dedicated protection mechanisms. This slide describes the 32-bit bus matrix of STM32H503 microcontrollers. The AHB5 multi-layer bus matrix in the center of the figure interconnects 7 masters and 6 slaves. Through multiplexers, the general-purpose DMA controllers have a direct access to APB buses, enabling them to efficiently service requests from APB peripherals. Accesses to internal SRAM memories initiated by the Cortex-M33 are performed through the SAHB port. The demultiplexer connected to the SAHB port selects the slave port in the main bus matrix according to the address SRAM1, SRAM2, SRAM3, backup SRAM. For SRAM1, 2, 3, latency is 0 when no other master currently accesses the SRAM. SRAM1, SRAM2, and SRAM3 are accessible on SAHB bus with a continuous mapping. Accesses to external memories connected to FMC or OctoSPI controllers are done through the D-cache, even if requests are marked as non-cacheable. These accesses can be data requests as well as instruction requests mapped in the external data region of the mapping. Note that fetching instructions through the SAHB and D-cache is less efficient than fetching through the CAHB bus and iCache slow port. This is the reason the iCache supports the address remapping capability. The GPDMA has a dual bidirectional master port, port 0 and port 1, to support concurrent transfers over these ports. Both master ports can access any memory mapped resource in the microcontroller, internal and external memories, internal and external peripherals. The port 0 is the default slave for AHB1 peripherals access. The port 1 is the default slave for SRAM1 access. Regarding the STM32H503, a direct access to APB1 and APB2 peripherals is performed through multiplexers and dedicated interconnect represented at the top of the figure. Thus, transfer requests initiated by these peripherals can be handled quickly by using this low-latency path. The SD and MMC controllers are master modules. They can access any memory, internal or external, because data written to SD and MMC is read from buffers in RAM and data read from SD and MMC is stored into buffers in RAM. The default slave is SRAM1 for both controllers. The Ethernet MAC integrates a dedicated bus master that has a direct access to internal memories as well as external memories. The default slave is SRAM 3. In addition to this presentation, you can refer to the following presentations: Instruction Cache or iCache, Data Cache or dCache, Flash Memory or Flash, Power Management or PWR, and Reset and Clock Controller or RCC.